Hello everybody, welcome to my YouTube video. In this video we'll discuss the concept of thermodynamics. I'll run you through some of the content and then we'll finish up the rest in another video. So we'll be talking about thermodynamics. So what would you say thermodynamics are? This is a study of the quantitative relations to do with the interconversions between forms of energy. So I know that might sound like a very difficult definition, but it's not so bad. So in thermodynamics, we're dealing with how certain parameters such as heat, work, temperature are related to the conversion between different forms of energy. So everything will make sense as we continue going. So the study of thermodynamics is initially an area of interest for those studying physics. However, pharmacists use some of the concepts. So the next series of lectures will be specifically for pharmacists. There'll be other lectures that will be more generalized, but then I'll attempt to explain the concept of thermodynamics from a pharmaceutical point of view. The study of thermodynamics is based on four main laws. So there are four main laws that guide the study of thermodynamics. The first law is called the zeroth law. Right? And then this law is quite straightforward. We say if two systems A and B are in thermodynamic equilibrium with each other, and then the system B is also in thermodynamic equilibrium with another system C, then that means all three systems are in thermodynamic equilibrium. So it's as simple as that. And then we have the first law of thermodynamics, which we'll talk in depth about in today's lecture. And then we have the second law, and then we have the third law. So we'll do those ones in depth. It's important for us to address some terminologies. Some words we'll encounter as we continue going through our series of videos. So the first terminology I thought was important to mention in the beginning would be energy. So how do we define energy? Energy is defined as the ability to do work. So the same definition we've been using still stands, right? And then the second definition, or the second terminology, is temperature. So temperature refers to the measure of the average kinetic energy that is contained by a system. So the temperature describes how much kinetic energy the individual particles contain. And so for that reason, when quantifying temperature, there's a formula that directly relates temperature and kinetic energy. So we say the temperature will be equal to 3/2 the product of the kinetic energy of the particles. So that's an important formula that you need to take note of. The next terminology we can talk about is work. So what is work? So work refers to the transfer of energy that can be used to change the height of a weight somewhere in the environment. So generally in classical physics we described it as being the product of force and distance, but in the context of thermodynamics that's also true, it also holds, but then I was trying to come up with a more generalized definition. The next concept we'll talk about is the concept of internal energy. So internal energy refers to the summation of all the energies within a system. So those would be our important terminologies. But then I've been sneaking in concepts such as system, environment, and so I feel like it's very important for us to describe what those ones mean also. So when you talk about a system, so a system is an area that is undergoing observation or where the thermodynamic process is occurring. We call that area a system. And then the environment is any other area apart from the area undergoing observation. Right? So by definition, we'll say a boundary will be the demarcation between the system and the environment. So that's the definition of those three terms. The first law of thermodynamics is very, very important. It's more applicable to physics, but then I'll try to make it as pharmaceutically relevant as possible. So this law is also called the law of conservation of energy. So we all know what the law of conservation of energy states. We say energy cannot be destroyed or created, but can simply be converted from one form to another. That's how we state the law, and that's exactly what you must state when they ask you to state the first law of thermodynamics. However, there are many ways of expressing this law. If they asked you to express it numerically, meaning with digits, then they expect you to express it using a formula. So when that happens, let's use an analogy. Suppose you had, let's say, a system, and then this system mainly consisted of a cylinder, like the one you're seeing there on the screen, and then suppose this cylinder had a piston that was fitted, and then let's say this piston was designed in such a way that it was frictionless, and then it is capable of moving depending on what's going on in the system. So if that's the case, let's introduce a heat source. After introducing that heat source, one thing you'll be able to see is that if inside the cylinder you had, okay, for the sake of simplicity, let's say we had a gas. Doesn't matter what the gas is, let's say we had a gas. So as we continue adding more heat, what do you think will happen to the system? So generally speaking, we know that when gases are heated, their kinetic energy increases. And then as the kinetic energy increases, the more the random walk, or the more the Brownian motion. And then when that happens, it causes them to exert pressure on the walls. And then they'll exert pressure against the piston. When this happens, they'll tend to push the piston some distance up, right? I'm sure most of you thought that's what's going to happen. And then since we said the piston is movable, it will displace some distance, x, as shown. So when this happens, what are you able to notice? So what you're able to notice is that when we add heat, right? Heat is our form of energy. That heat will do two things to that system. One, it will cause that system to gain in internal energy. We saw that gain in internal energy when we saw the kinetic energy of the molecules increase. And then we saw it also when the random walk increased, and when also the pressure exerted on the walls increased. That was signifying a gain in internal energy. What else did we see? We also saw that because of the increase in internal energy, we saw that these particles eventually caused that system to displace the piston some distance x. So for those who remember their physics, when anything is displaced some distance x, that's literally the definition of work. So that system did work on the environment. Now, when we talk about thermodynamics, there are other important parameters that we need to consider. One of the most important parameters that we need to talk about are the thermodynamic processes. First thermodynamic process is the one we are calling isothermal processes. The second type we'll call them adiabatic processes. The third type we'll call them isobaric processes. And then the last type, the fourth type, we'll call them isovolumetric. By looking at the words, it's pretty easy to see what they mean. So an isothermal process will be a thermodynamic process that is occurring in a manner that temperature is kept constant. The second type are the ones we call adiabatic. So an adiabatic process will be a type of process where heat is not lost or gained, right? And then an isobaric process. An isobaric process will be a process where the pressure is kept constant. And then the last type is called an isovolumetric process. Isovolumetric process, you guessed right, this is a type of process where the volume is not allowed to change, right? So let's go back to our thermodynamic processes. So the first thermodynamic process was the one we said was an isothermal process. Temperature is not changing. So because the temperature is not changing, one thing you'll be able to see is that the internal energy of the system is not changing, because we said internal energy would depend on the kinetic energy, right? So if the kinetic energy is not changing, the temperature is not changing, that means the internal energy is not changing. Remember that when we said quantity of heat equals internal energy plus work done, when we discussed internal energy, we're not talking about the absolute value. We're talking about the change, the difference, since it's an example of a state function, right? So a state function, for those who don't know, this is a value that depends on the initial and the final conditions only, right? So we'll be able to see if the internal energy does not change, the internal energy therefore will be equal to 0. And then if the internal energy is equal to 0, it can allow us, or will be allowed to rewrite this formula. So instead of saying quantity of heat equals internal energy plus work done, we could say the quantity of heat will equal the work done, right? Yeah, so that's one thing we'll be able to see. So that's how the first law is in an isothermal process. What about an adiabatic process? In an adiabatic process, heat exchange or work is not allowed, right? So this system is completely isolated in such a way that heat is not allowed to leave the system, neither is it allowed to enter the system. So if that's the case, that means the first law of thermodynamics has a different meaning for an adiabatic process. We could say the quantity of heat will equal what? So the quantity of heat will be equal to 0, right? To be equal to 0 because heat is not allowed to leave or enter the system. Therefore, the change in internal energy will be equal to the work done. Are we getting how the connection is? Then the next type of process are the isobaric process. So when you have an isobaric process, the same, let's say the full form of the first law of thermodynamics holds. So we'll say the quantity of heat will be equal to the change in internal energy plus the work done. And then in an isovolumetric process, in these types of processes, one thing you'll be able to see is that volume is not allowed to change. So let's go back to our analogy. So when we look at that example we had, suppose the piston is put in such a way that it's not movable. If it was not movable, one thing we'll be able to see is that volume cannot change. If volume cannot change, that means that system cannot do work, right? If it cannot do work, then work done equals 0. Therefore, the quantity of heat will be equal to the internal energy. So those are some of the most important parameters you should be able to see. There are 3 types of systems. The first type are called open systems. Second type are called closed systems, and then the third type are called isolated systems. So what's an open system? An open system is a system where the exchange of mass, heat, and work are allowed. So an example of such a system would be a cup of coffee left on a table. One thing you'll be able to see is that the liquid, the coffee, can evaporate, therefore there's a loss of mass, and then as it evaporates, it's carrying heat with it. So that's an example of an open system. A closed system, this is a type of system where only work and heat are allowed to be exchanged. So suppose you had a cup of hot water. That cup of hot water, suppose it was covered. If it was covered, even though the liquid evaporates, one thing you'll be able to see is that no mass will be lost. However, heat will be lost to the environment. That's an example of a closed system. And then an isolated system, this will be a system where neither heat nor mass nor work are allowed to leave the system. So those will be our types of systems. So that's pretty much what I had for you in the first video. Yeah. So if you liked the content that you saw, then don't be afraid to like and subscribe, and then in the next lecture we'll continue with the other topics.